In this video, I'd like to go through several examples so that we can practice using U-substitution. A few things before we get started. All of these will be indefinite integrals, so we already discussed in the last video what to do when you do have bounds, and I would just want to focus on the technique of U-substitution here. And I'll also say that in watching this video, it's probably a good idea for you to pause it so that you can try and figure out the substitution yourself to get that practice. Okay. To start with, first example, let's look at the integral of x squared plus 1 raised to the fourth. So again, my strategy here is to figure out an appropriate choice of u. And we saw before that often if I have a composite function, I might try letting u equal what we think of as the inside function. And my hope is that the derivative of my choice of u is also present up to constant multiples. So when I look at this here, I see the composite function of x squared plus 1 all raised to the fourth. So I'm going to let u equal that inside function. Then du is the derivative of that 2x dx. And I have x dx. I don't have 2x dx. Turns out that doesn't matter because from this I can see that 1/2 du is equal to x dx. So when I replace x dx with du, I have to include a multiple of 1/2. I can either write that inside of the integral or outside. So this now is 1/2 the integral of u raised to the fourth power du. Now I find the antiderivative. That becomes u to the fifth over 5. Still times 1/2 plus my integration constant. And remember, the important final step is we're not done until we rewrite this in terms of x. So that leaves me with 1/10. And then we said u was x squared plus 1. That's raised to the fifth, and then plus my constant. Another example. Suppose we're looking at the integral of 1 over 3x plus 1. Now, this one might be a little confusing at first in the sense that what do we choose u to equal? Notice that you never want to make the assignment u equals x because you're simply going to get the same integral just written in terms of u. So I don't have a lot of choices here, but maybe the one thing I would think of is this would be a much simpler integral if the variable was all we had in the bottom, just simply u. If we let u equal 3x plus 1, the derivative of u is 3 times the derivative of x. Like we saw before, I can deal with that by saying then 1/3 du can replace dx. So we get 1/3 the integral of 1 over u du. And remember, the antiderivative of that is the natural log, importantly, of the absolute value of u. So we have to include that absolute value in there. And finally, rewriting it in terms of x, we get 1/3 natural log of absolute value of 3x plus 1 plus c. All right, example 3. We look at the integral of the natural log of x divided by x. And what jumps out at me here is that I have a 1 over x in there, and that is the derivative of natural log of x. So if we choose u to equal natural log of x, then du is 1 over x dx. So this integral now can be expressed as simply the integral of u du, giving us the antiderivative of u squared over 2 plus a constant c, which is the same thing as the square of the natural log of x over 2 plus c. So this next one is a little bit harder. I want to go through this example here. I'm also going to go through this example for the next technique we cover, integration by parts, and it'll be a nice comparison to think about the different ways we can approach this. So the hard part about dealing with this with regards to U-substitution is that it involves a trig identity that may or may not be one that we are readily used to remembering. So the trig identity is, I'll put this over to the side here. Sine squared of x is 1 minus cosine of 2x all over 2. And I will say the main reason that I do in fact know that trig identity is for dealing with integrals like this. So it is handy to remember that for this purpose, but I'll also point out if you prefer the technique of integration by parts on this one, which doesn't involve a trig identity, that's fine as well. So if I know that identity, I'm going to rewrite this integrand as 1 minus cosine 2x all over 2. And notice that now this composite function comes in for this cosine of 2x. So what I can do at this point is at least rewrite this as the integral of 1/2 dx minus 1/2 the integral of cosine 2x. And for this first part, we don't need U-substitution. That's just going to give me x over 2. But for the second part, I want to use U-substitution. So I'm going to let u be 2x, then du is 2 dx. So I can replace dx with du as long as I put in a constant multiple of 1/2. So with the 1/2 that's already out front, I'm bringing in another multiplier of 1/2. So this really becomes minus 1/4 the integral of the cosine of u. We have x over 2 here. Antiderivative is now going to give me minus 1/4 sine of u plus c. And I'll point out, you might be wondering why I didn't put a plus c up here. That would have been fine as well, but essentially I know that I have to have some representation of an additive constant by the time I get to the end of this, and I'm just holding off doing that until I got to this last integral. And we're not done because I need to have it all written in terms of our original variable x. So if I now put back in u equals 2x, then I've accomplished that. So a very similar integral would be that of cosine squared of x. And I'll point out that we have a similar identity that says cosine squared of x is in fact 1 plus cosine of 2x over 2. So I would handle that in a very similar way with U-substitution by rewriting the integrand. All right, now that we're talking about trig functions, we can also use U-substitution when we have a product of certain trig functions. So if I had, say, cosine squared of x times sine cubed x. Now, if we were teaching this synchronously, I would actually pause here and have everyone in the class try to solve this, because what's interesting is that a lot of people try different things for u, and it doesn't quite work out. And so it's usually useful to see that this is a tough integral. And like I said, I'm going to go through the answer, but we wouldn't have that time to pause and realize, okay, there's lots of potential choices for u. It turns out if you let u equal cosine squared or you let u equal sine cubed, the problem is that what is left over in the integrand is not equal to the derivative of our choice of u. So we want to try lots of different things. And in general, what it's going to come down to is trying to rewrite this integrand using trig identities. And in particular, I'm thinking of the one that you really do want to remember, sine squared of x plus cosine squared of x is equal to 1. Try to make that a little bit clearer. So even with that hint, notice that I have two potential ways of rewriting that. I can either try to rewrite cosine or I can try to rewrite sine. So a couple things to consider here. If I were to rewrite cosine squared as 1 minus sine squared, the problem is that my whole integrand would involve sine, And any derivative of sine is going to involve cosine, right? Any derivative of some sine function or function of sine. And I would have removed all of the cosines. So instead, because I really want both trig functions to still be there, I'm noticing that cosine squared times sine cubed can be written as cosine squared times sine squared times sine. And now I can see that I could still have a sine of x present even if I rewrite my sine squared of x. So I'm thinking of the fact that sine squared of x is equal from this trig identity to 1 minus cosine squared of x. So this integral is cosine squared of x now times 1 minus cosine squared of x times sine of x dx. At this stage, I have not used U-substitution. I'm simply rewriting the integrand. But now I can let u equal cosine of x. If I let u equal cosine of x, du is now going to be minus sine of x. So when I replace my sine x dx, I need to make sure that I put in a minus 1. So now I can say that the integral we had is equivalent to minus 1, the integral of u squared times 1 minus u to the 4th du, which is minus the integral of u squared minus, sorry, this should have been a squared, and then minus u to the 4th. So u squared times the quantity 1 minus u squared is going to yield that u squared minus u to the 4th. And now I'm ready to anti-differentiate. So we get minus the quantity u cubed over 3 minus u to the 5th over 5 plus my integration constant. And finally, reverting this back into functions of x, I could express this as cosine of x to the 5th over 5 minus cosine of x cubed over 3 plus my integration constant. Okay, so final answer. And we could check that, in fact, when I do take the derivative of that, it gives me exactly what I started with. And so for the remaining few examples, again, I want to kind of point out that we might have to be a little bit crafty with our choice of what to choose, choice of u here. So if I have the integral of x over square root of 1 minus x to the 4th, a completely natural choice for u would be to say, let's just let u equal 1 minus x to the 4th. In that case, du would be minus 4x cubed. So if we had an x cubed up top, that would be no problem. We could put a negative 1/4 out on the front and we could deal with that. But we don't have x cubed, and we can't really force an x cubed in there. So what I want to do is kind of go back to the start and think, what else could I use? So what I start to notice is that my x that I have in the numerator, that would be the derivative if u were instead x squared. So at first glance, it might feel like, well, we don't have an x squared, but we do, because I can think of this now as 1 minus the quantity x squared squared. Of course, that's a silly way to write that. But what's helpful about that is that's starting to remind me of the derivative of a function that I know, and that's the derivative of arcsine. So I'm keeping in mind that the derivative of arcsine is 1 over root 1 minus x squared. And so that's really going to be the connection here. So the non-obvious choice of u is to, in fact, let it be x squared. Du is now 2x dx. And consequently, that dx that I have, 2x dx, I didn't write that. So dx, or x dx, is now 1/2 du. So rewriting this, I'm going to now have the integral of 1/2, so I'm going to put the 1/2 out front, the integral of now 1 over the square root of 1 minus u squared, which gives me 1/2 arc sine of u plus c. And then finally, because u is x squared, we get 1/2 arc sine of x squared. So sometimes the first thing you try might not work out, and that's part of the practice. So I think with this topic in particular, really practicing with those textbook integrals to get that intuition about maybe some non-standard choices that you could make. Another example to see this is, I guess I'm just going to call this the, let's see, this is the integral of x over x minus 1. So this is a tough one because everything we've seen so far was very clearly a composite function. In some sense, we looked for the derivative of that expression there. And I also pointed out that it's not ever going to be useful to make the substitution u equals x, because that just simply rewrites your integral. So if I told you that we could use a u substitution here, kind of the only choice would be to let u equal x minus 1. But that doesn't at first glance seem like that's going to be useful. Du would then be dx. And if I think about trying to rewrite this, I have the integral, I can put u here and put du here, but it seems like this is going to be a problem. You don't ever want to end up with two variables in your du integral. So what we haven't seen before, though, that I can take advantage of here is let's try to rewrite that x in terms of our new variable. And what I mean by that is we know that x minus 1 is equal to u. If I add 1 to both sides, that tells me that u plus 1 is x. So we could put that there. Now, structurally, this, again, at first glance, looks very similar to what we had above. But there's an advantage here. Now that I have that addition in the numerator, I can break this up into two separate fractions. And I couldn't do that with that subtraction in the denominator. So I have the integral of u over u. It's just the integral of 1 plus that of 1 over u. And so now I can write this as the antiderivative of 1 is going to be u. And then I add to that the natural log of the absolute value of u. And then finally replace everything with x minus 1. So we end up with x minus 1 plus natural log of x minus 1 plus c. Now, a question that I've often been asked before that I just want to address here, another correct way to express what you have here is x plus natural log x minus 1 plus c. So you could take that minus 1 and absorb it into this arbitrary constant. So this would be fine, but that would be correct as well. So now let's look at the integral of 1 over 4 plus x squared. Again, there's not a lot of choice here if somebody told you you could use a U-substitution. So instead, what I'm going to rely on is some instinct. So starting to remember some important relationships between a function and its derivative. What this reminds me of is that if this were the integral of 1 over 1 plus x squared, that would just give me arctangent of x plus c. But of course, that 1 is significant, and we have a 4 here. But that does at least motivate me to want to maybe factor that out. So 4 plus x squared, I can write as 4 times the quantity 1 plus x squared over 4. So if I factor a 4 out of the denominator, I can write that with a 1/4 here. Now notice that 4 is 2 squared. So this is now 1/4, the integral of 1 over 1 plus, and I can write this as the quantity x over 2 squared. So now let's let u equal x over 2, in which case du is 1/2 dx, and therefore 2 du can replace dx. So putting that in here, I have 1/4 that was out front of that integral. I'm introducing a 2 from this here, times the integral of 1 over 1 plus u squared du. So this constant out front simplifies to 1/2. The antiderivative is arctangent of u plus c. And I finish by replacing u with x over 2. And finally, my last example in this video is another one in which we can rewrite the original integrand. So if we were asked to integrate tangent, it's not obvious what function has derivative equal to tangent. However, you can replace tangent with sine of x over cosine of x. This is useful because we know that, again, the derivative of sine and cosine, those are going to be plus or minus sine and cosine functions. So those are related to one another. Now, in terms of choosing which one of those to be u, you wouldn't ever want du to be in your denominator. So I really want the denominator to be representative of u, in which case the derivative is minus sine x dx. So minus du can replace sine x dx. So this integral of tangent that we started with now equals the negative integral of 1 over u du. So we get negative natural log of absolute value of u. And finally, negative natural log of the absolute value of cosine of x plus c.